I'd like to thank Brilliant.org for sponsoring this video.
Hi, welcome to Astro Journey UK. In today's video I'm going to be talking about drizzling, what it is, why we might need it, how it works and how to do it in PixInsight. This follows on from a video a couple of weeks ago where I tried a camera which was paired with a telescope, which resulted in undersampling, just to see what would happen in the real world. And a number of you commented saying, well, basically you should use drizzling. So I figured I'll just cover drizzling in this video instead. So if you're interested in finding out more, then keep watching. So what is drizzling? The term drizzle refers to a process officially known as variable pixel linear reconstruction, so you can see why they decided to call it drizzling instead. It's an advanced technique for combining dithered and undersampled data to improve your quality of your astrophotography images. The term drizzling was inspired by the way that when rain falls onto a surface, it gradually builds up over time to form a larger hole. You'll also notice a little bit later on in PixInsight when we talk about drops, and that's where kind of the term drop comes from within the dithering side of things as well. So it was invented in 1996 by the Hubble Deep Field team to overcome some issues that they had when handling undersampling image data with their deep field image, and drizzling integration helps improve the overall resolution and correct some geometric distortions caused by undersampling, basically removing blocky stars. There's a bit of an impact in terms of noise of the overall image. Some things sort of say that it actually decreases the noise, and some people are basically saying that it increases the noise. So from my research, I couldn't actually see sort of one way or the other, but we'll have a look at some images as well, and you'll be able to understand and sort of make that decision yourself as to whether or not it's increasing, decreasing the noise, or not making any difference at all. Now, you might be wondering why we need to drizzle in the first place. The main reason for this, which prompted this video, was when your camera and your telescope combination result in a thing called undersampling. This occurs when basically the number of pixels that you have in the image is insufficient to accurately capture the detail of the object you're imaging itself. So for example, any stars that you have in the field of view, when you actually zoom into them, you'll find that those stars are actually sort of slightly blocky and pixelated, and so therefore you haven't got the nice round definition of the stars themselves. There are fundamentally insufficient pixels on the sensor to be able to capture that detail. This is sort of linked to the focal length that you're using and the pixel size itself. So drizzling helps to remove that pixelated view by increasing the overall resolution of the image itself, of that final image, and you can then sort of build up rounder stars and more detail from the detail that you have. So how does it work? So drizzling is an algorithm that involves combining multiple low-resolution images into a single high-resolution image. The goal of this drizzling is to increase the effective resolution of this image to beyond what is possible with a single exposure. The drizzling algorithm works by sort of first dividing each of the low-resolution images into a sort of grid of smaller pixels, and then for each of those pixels a higher resolution output image can be created. And this algorithm is fundamentally sort of computing the weighted averages of all of these smaller pixels to be able to interpolate what the values of the output image actually will be. One thing I forgot to mention before, with all of this, when you're actually capturing your data in the first place, you have to use dithering. So you should be using dithering anyway, just to avoid problems with walking noise in your images. If you've got multiple hours of exposure and you're not dithering, then you'll get some really nice, nasty streaks of noise throughout your images. Sadly, something I suffered with fairly early on when I got into this hobby. So overall, the drizzling algorithm is a powerful technique for increasing the resolution and detail of your astronomical images, and it's widely used both in the amateur astronomy area as well as professionals, for example the Hubble Deep Field team. As this video has been focusing a lot on the drizzling algorithm, I think now is a great time to mention my sponsor, Brilliant.org.
Brilliant is a fantastic website for anybody wanting to learn about a variety of STEM subjects like physics and computer science. Whether you're a complete beginner or have a more advanced understanding, then Brilliant is for you. One lesson that I've been working through recently has been on the introduction of neural networks. A couple of lessons around computer vision and how computers process and understand image data have been quite applicable. In this lesson, I got a taste of some of the intricacies around how computer vision works, the difficulties involved in teaching computers to see and process those images, and I learnt how images are stored as an array of numbers and learnt how some of the aspects of this are used to extract the information from these arrays to process the images. So if you're interested in trying this, then you can get a free 30-day trial by heading to brilliant.org/astrojourneyuk, and the first 200 of you will get 20% off Brilliant's annual subscription.
So what we're going to do now is we're going to move over into PixInsight, and I'll talk you through the drizzle process whilst doing your sort of weighted batch pre-processing or integration of your image data.
So let's open up weighted batch pre-processing script. So this is where we're going to be doing our drizzling, and you'll typically want to be doing it here anyway because you're going to be doing all of your image integration, stacking, etc. I've already been stacking these images and playing about with this, so you'll see that there's lots of sort of master bins and things. If you're not familiar with this, there's plenty of tutorials out there. However, yep, you would need to add your bias frames into here by sort of clicking on the plus icon, add in the bias frames, same with the darks, flats and the lights. Once you've actually produced those and PixInsight's created master dark files, it will then begin to use those if you're stacking with the same camera each time, so that's quite nice. Yeah, all of the images are selected in here, and then it's in the post calibration tab where you've got the drizzling configuration. Normally it's turned off and this is what it will look like, so you'll just click on the enable button and you've got a number of settings here, and I'll just talk through what those settings are. So here you've got scale. If you did just scale 1, it's not going to increase the resolution of your image in any way, shape or form because it's going from the current resolution to the same resolution but drizzling. So you might want to set the scale parameter to 1. Situations when this might be appropriate is if you have input images that are already optimally sampled and have a high resolution, then pixel shrinking might not be necessary, and setting the scale parameter 1 can actually preserve the fine details and avoid unnecessary artifacts. Additionally, the input images might have different pixel scales or resolutions, then setting the scale parameter 1 to 1 can ensure that the original pixel scale and resolutions are maintained in that final image. This can be useful if you're combining images from different telescopes and instruments with different pixel scales and combining those into a single image. So most people actually set this to 2. You can sort of then start to push it into 3 and 4 and things like that to get a much larger image, but I think at the end of the day you're pushing beyond the benefits of actually how drizzling is going to be able to increase the resolution of your images using the dithered data. So onto the drop shrink parameter. So in drizzling, drop shrink parameter controls the size of the output pixels in that final drizzled image. So drops come as a metaphor for like photon drops hitting the sensor, hitting the individual pixels within that sensor, and it determines how much of the subpixel data from each input image is shrunk and then combined to create the output pixels in the final image. So you can have with drop shrink parameters, you can have a value of between 0 and 1, where 1 means no shrinking, i.e. the output pixel is equal to the size of the input pixel, and the value of 0 means maximum shrinking, so the output pixel is equal to the size of the drizzle footprint. So to understand how this works, let's kind of consider a bit of an example here, and I can use the image from this particular article, which is from the people that made the algorithm in the first place. So they've got a nice diagram here that shows the input pixels here. You've got a 2x2 input pixel. You've got a little blue box here which is showing the drop size, so they've shrunk the pixels. And then it's being mapped onto the output image. It's drizzling by a factor of 2, so the 2x2 input pixels are then scaled up by 4x4 pixels. So you can see here it's been rotated slightly, so there's a geometric transformation going on here, but if this was exactly lined up, you can see that these lines will line up roughly with or line up with this 4x4 output matrix. If we set drop shrink parameter to 1, i.e. no shrinking, then the output image is a 4x4 pixel image, would be formed of these pixels here, and you can see them in red here. And this would result in a final image with a pixel scale that's half of that of the original image. However, if we were to set the drop shrink parameter to 0.5, and this is sort of an indication of that, then the output pixel in the 4x4 image will be formed of combining subpixel data from the 2x2 pixels in this particular grid format. So you can see when it's actually then running through the algorithm, it's taking the values of intensity of this subpixel, and you can see where they're overlapped, so you can see which pixel will have the relative brightness from that drop subpixel. So in general, if you want to increase the resolution of the final drizzled image, you should set drop pixel value parameter to a value less than 1. If you want to preserve the original pixel scale of that image, then you should set the drop shrink parameter to 1. Basically, in summary, there's a lot going on with the algorithm, and probably really in reality, unless you know what you're trying to do in terms of combining images from different telescopes and different focal lengths and all of those sorts of things, and you're trying to create an image of 1 pixel scale, then you would set scale to 1, for example. If you're trying to pull some more detail out of an undersampled image, then you kind of set it to a scale of 2 and drop shrink of around 0.9, which is the default, but you can start to play about with this and see whether it helps gain any more detail through an enhanced resolution from using the dithered and drizzled data. So onto the functions now. These are also referred to as kernel functions in the documentation. Sometimes you see those terms used interchangeably. So if you see kernel or kernel function or function, they're the same thing in this particular context. So you've got a number of options here: square, circle, Gaussian, and var shape. I'll just go through and just talk a little bit briefly about what these different things are. So the square function is a simple box-shaped function that treats all subpixels within that drizzled footprint as equal contributors to that output pixel. This function is useful when subpixel data is evenly distributed within the footprint, or where the input data has a high signal-to-noise ratio. If you've got you want to use a circular function, similar to the square function, but it applies a circular weighting to each of those subpixels within that drizzling footprint. The function gives more weight to subpixels that are closer to the center of that footprint, which can help to reduce things like ringing artifacts in the final image. When you're using the Gaussian function, this applies a bell-shaped weighting function to the subpixels within the drizzling footprint. This can give more weighting to subpixels closer to the center of the footprint, a bit like the circular one, and there's less weight to these subpixels further away from the center. This can help reduce the impacting of noise and other artifacts in the input image and produce a more smoother and natural looking final image. There's also var shape, and then you can see that there's many different options here, so you can go to town with these things, and I think really what you need to do is kind of test them out, and I've got some test images from drizzled data as well to see with an example what this stuff looks like. But with the var shaped function option, this drizzling process allows you to adjust the shape of that kernel function based on local variance of that input data. And the idea behind this var shape is to adopt a function to the characteristics of that input data itself to produce a final image with minimal artifacts and a higher signal to noise ratio. This var shape, when it's enabled, allows you to calculate the local variance of the input data at a point within that drizzling footprint. This function is then modified on the basis of that local variance, a larger function to the regions with higher variance and a smaller function to the regions of low variance. This allows the kernel function to be tailored to specific characteristics again of the input data, producing a final image that's optimized for both resolution and noise reduction. This option can be particularly useful for people when you're working with data that has a variable noise level, or when you're trying to extract finer details from low signal to noise ratio images by adjusting this kernel function on the basis of that local variance. So I've realized in talking about this that there's a lot of talk about variance and local variance and things like that, and what do those things really mean. So when the algorithm's actually looking at the pixels and it's got an area of the image that it's drizzling, it's looking at the difference in when they say variance, it's looking at the difference in contrast. So if there's a high variance, then there's a high difference between sort of low pixel values and high pixel values, i.e. light areas and dark areas, indicating more contrast. So when there's high variance, then you apply one particular type of function, and when there's low variance, i.e. low contrast, then you'd apply a different function. It's worth noting that this var shape can be computationally expensive. Basically a long-winded way of saying if you use this, it's going to take longer to actually drizzle your image data. So yeah, just bear that in mind as well. When you actually do change these to using the var shape, it then enables this grid size parameter, and this is fundamentally used to sort of determine the size of the grid that's used to divide the output image into smaller regions, and this grid is applied to the drizzle algorithm to the input data within each region of the output image. So it's an important parameter in terms of this drizzling process because it affects both the speed and the quality of the output image. So a smaller grid size will result in a higher resolution output image, but this will require more processing time, more memory. Conversely, a larger grid size will result in lower resolution output image, but will be faster and require less memory. So just to finish off sort of actually running through this drizzling process, so we've got all of the lights, flats, darks, bias frames. We've enabled drizzling here, set the scale to 2, kept the drop shrink value to 0.9. You will need to set the output directory in the same way that whenever you're using weighted batch preprocessing to integrate and calibrate all of your frames, you need to provide this output folder. Once you provide the output folder, you just hit run. You'll be prompted with a screen that says, here's how much disk space I'm going to need for this particular activity. Hit continue, and then it will run through that whole process. In terms of the output image and the location of that output image, you'll find that in the master folder. Here you'll find a lot of additional files. So these are the standard integrated files. So you've done all of the standard registering, calibration, and integration as part of weighted batch preprocessing, and you will end up with these files. And then anywhere where you're doing drizzling of that image data as well, you'll see that there are some drizzle files that are created here as well. So this is one that's just literally being created that you've just seen there, but when I was experimenting with 3 times drizzle, you can see that there's the output image there. Each time you change and test the drizzling algorithm, you'll get a copy of the new file. So each time you change it, it'd be sensible to just rename that file so that you know exactly what it is, and then you can then do your own comparisons in terms of what looks best for your particular situation. So on to the final part of this video is just a brief comparison of the different drizzling functions. So this image that we've got in the top left here, you can see is no drizzle. This is a 1:1 ratio image, and comparing that with the 2 times drizzle ratio 1:2, you've got the same field of view. Kind of obvious here in terms of we've drizzled it by 2 times, so therefore there's 2 times the amount of detail. If you move into 1:1 ratio, yep, you can see still a level of detail. It's really when you get to, if you do like 5:1 both of these images, then you can see the difference in terms of the stars and how few pixels there are in terms of undersampled images there. And then when you move into the same magnification of this particular image, the stars have got a little bit more detail and definition around them. So that's kind of the benefits of drizzling. When I've actually then begun to compare this to the different algorithms, I think it's been a bit of a struggle to see really where the differences are. Maybe it's just the particular type of image that I've got. There's only about 10 subs worth of drizzled integration data, so it's not a perfect data set by all sense or stretch of the imagination. Yet you've got the circular function method here, and then the square integration method in the bottom right hand corner. In terms of, so they're exactly the same field of view, same level of magnification. I can't really see any significant difference in terms of how things look. I was looking at the stars to see whether the circular approach versus the square approach results in different star details, and actually you can see maybe there is a bit of a difference with the look of that particular star, maybe, but my goodness, you have to zoom in this far to actually see a significant difference at the end of the day. So it's yeah, I don't think it's really worth, by the looks of things, worrying too much about what drizzling algorithm you're actually using to get the best out of the drizzling system itself. So it's a good example of just using the defaults are going to be absolutely fine for most use cases. So that's the the differences between square and circle, if there are any differences that are perceivable. Then we can pick up the 2 times Gaussian 16 grid and comparing that to the square. Again, it's very difficult at this level of magnification to kind of see any difference. Kind of looking for differences in noise in the image, and you can see that, I mean, there is noise in the image in the first place because it's only 10 exposures, but yeah, differences in the shapes of the stars or detail that's been pulled out from this particular set. Yeah, maybe in this instance I need a lot more data to be able to highlight these differences. I think they're just too difficult to actually make out in this particular situation. And then finally the var shape B1 approach. And compare that to the square, back to the same level of magnification. Maybe there's a touch less noise in the image, but again, it's really difficult to see. There might be a little bit more sort of contrast in these areas, ever so faint differences. But again, you've got to really study the images to actually see any significant change here. Kind of magnify to 5:1 ratio. Yeah, it's really difficult to see any differences there. So I think I'll leave it at that. This video has been much longer than I was planning on it being, so apologies for that. Thank you very much for watching, everybody, and clear skies.